A good starting point for trying to understand fluid flow is something called Leibnitz theorem. So all of our conservation laws basically take the form of a time derivative of some quantity. And that some quantity is an integral. So it might be the mass, which is an integral of density over volume, or it might be an integral over the total linear momentum in a system, or whatever. So Leibniz theorem is a specific way of trying to think about rates of changes of integrals with respect to time, where both the integrand and the limits might change with time. So think about a volume or a chunk of volume, like a control volume, where the control volume might move while you're trying to do the integral. That's what Leibniz theorem is all about. So Leibniz theorem is written in one dimension, and then I'll show you soon that it can be extended to 3 dimensions to form basically the Reynolds transport theorem. So here's the idea. So I want to take the rate of change, with respect to time of an integral of f. F is a function of multiple variables. It's a function of x and time. The integral will be done over x, but the derivative will be done with respect to time. So basically, after I'm done integrating over f of x and t over x, I'll be left with the result of that integration, which will be some capital F as a function of time. And I'm looking to take the time derivative of that function f of t, capital F of t, with a set of limits that themselves change with time. And that's the tricky part. But it's actually not too hard to handle this case. So here's what we do. So I think the easiest way to do this is to actually make a plot of what's happening here. So what it means to take the derivative of that thing with respect to time is to calculate how much does capital F change when I go from one time step to a small time step later. So let's draw that plot. So here's a plot where I have an initial function f of x evaluated at time t. So I'm going to draw the function as a function of x, but that's only at a particular time t. And I would like to do the integration from its lower limit a, which is at some location at time t, and its upper limit b, which is at some location at time t. And then look at what changes when I move a distance delta t away. So if I redraw the graph a time delta t later, then the function itself will have changed a little bit potentially. So f of x and t becomes f of x evaluated at t plus delta t. And that function might look a little bit different at that time. In addition, the limits will have changed. And so instead of evaluating, like the left limit, let's say at a of t, it'll now be evaluated at a of t plus delta t. And similarly with the upper limit b will have shifted over to potentially some amount. And so if I think about how the function f has changed, so I need to calculate the change in f relative to the change in time. How did that function change? So there's actually 3 components to how it changed. So one is that the function itself changed. So the function may have shifted up or shifted down in certain locations. And so the change in the actual function over the time, t plus delta t to, t is f of x evaluated at t plus delta t minus f of x at t. That's how much it changed. And most of the change, like if I'm doing an integration over the entire function, most of the change is, is over the range from a to b. A to b hasn't changed that much in an infinitesimal time, so like most of that change is there. But then there's 2 other contributions to the change in the total integral. So like, for example, if I move the right boundary, b, that's associated with b, and I shift that boundary to the right, then I'm adding a certain amount of area to the one side. And the amount of area that I add is an amount that's almost equal to the total value of the function at the right boundary times the width or the distance that the right boundary has moved, that I'll call delta b. And then similarly on the left side of the graph, if I shift the boundary a over to the right, I'm subtracting a portion of the integral that was being done. So there's less area on the left side of the graph now. And so the amount that it's reduced by is approximately equal to the value of the function at that left boundary times the distance to the right that I've moved that boundary over. And then to take the actual, if I'm looking to calculate that derivative, all I need to do is turn the little differentials that we have and take the limit of, delta t going to 0. So like what you'll see is that actually creates a series of derivatives, partial derivatives with respect of, the function, or partial derivative of the function f with respect to t, and then two other ones that have to do with the derivative of the limits with respect to time, which in other words is actually the velocity. So how quickly those limits are moving, the velocity of those limits actually determines part of the value of the derivative of the total of that integral. And so you can recognize that, for example, the limits are only a function of t, like their position is only a function of time, and so instead of being a partial differential with respect to t, those are total differentials, or normal, ordinary derivatives. And you can write out, Leibnitz theorem in terms of a local derivative, which is like the integral, from a to b of the partial derivative df dt integrated over x, plus the two contributions from the limits. All right, so to summarize, when we're done, what we find is Leibniz theorem tells us that to take the rate of change of an integral where the limits are changing in addition to the integrand, there are three terms. One which is a local derivative of the function, like a partial derivative inside the integral, plus a term that has to do with movement of the right boundary, minus a term that has to do with the movement of the left boundary.